In this video, we're going to look at a few more examples of improper integrals with discontinuous integrands. Here we have integral from 0 to 1, 1 over x squared dx. The question is, why is this an improper integral? Well, the reason is 1 over x squared, the integrand, blows up to infinity at x equals 0. You can see that how the curve is approaching the y-axis as x approaches 0. So what we have is integral from 0 to 1, 1 over x squared dx. That's equal to limit t approaches 0 from plus side, integral from t to 1, 1 over x squared dx. Let's rewrite this. We have limit t approaches 0 from plus side, integrate from t to 1, x to the minus 2 dx. Now I want to emphasize this. Notice that the discontinuity is at x equals 0. And we replace that discontinuity by t, then take the limit as t approaches 0 from the plus side. Okay, let's do the integration. We get integral of x to the minus 2, reverse the power rule. We get x to the minus 2 plus 1 is negative 1. Divide by negative 1. Evaluate it from t to 1. And don't forget to put a limit. Limit t approaches 0 from the plus side. That's going to give us limit t approaches 0 from the plus side, negative 1 over x, evaluated from t to 1. Now apply fundamental theorem of calculus. We get limit t approaches 0 from plus side. Put the upper limit in. The upper limit is 1. We get negative 1 over 1 minus 1 over t. That gives us negative 1 plus 1 over t. And take the lim as t approaches 0 from plus side. So what do we get? Well, we have limit t approaches 0 from plus side of negative 1 plus 1 over t. That gives us, well, the limit of negative 1 as t approaches 0 from plus side is just itself, negative 1. The limit of 1 over t as t approaches 0 from plus side will be infinity. So the answer is infinity. Diverges. So our conclusion is that the integral from 0 to 1, 1 over x squared dx goes to infinity. That means this integral diverges. All right, let's look at another example. Here we have integral from 0 to 1, 1 over root x dx. Why is this an improper integral? The reason is because the integrand, 1 over root x, blows up at x equals 0. And so we replace this lower limit by a variable, say t, and then take the limit as t approaches 0 from plus side. Let's do that. So we have integral from 0 to 1, 1 over root x dx. This is equal to limit t approaches 0 from plus side, from t to 1, x to the negative 1/2 dx. This is equal to limit t approaches 0 from plus side. Now, what do? Well, we reverse the power rule. So integrating x to the negative 1/2, we get x to the negative 1/2 plus 1 is 1/2. And divide by 1/2 is the same thing as multiplying by 2. Evaluated from t to 1. And that's going to give us, put the upper limit in, and don't forget the limit t approaches 0 from plus side, 2 times 1 to the 1/2 minus 2 times t to the 1/2. And that's going to give us 2 minus 2 times 0 to the 1/2. Because we're just plugging in t approaches 0, we're plugging in 0. The answer is 2. So the integral from 0 to 1, 1 over root x dx is equal to 2. Converges. Why is it that this integral converges? And so the integral from 0 to 1, 1 over root x dx converges, and the previous integral, integral from 0 to 1, 1 over x squared dx, diverged. So let's examine that. Let's fill these in. So this is equal to infinity, diverges, while the integral from 0 to 1, 1 over root x dx, converges. So we're going to investigate that. So the way we do that is we look at this in the pattern of a p integral from 0 to 1, 1 over x to the p dx. And our goal is to find the values of p that make this integral converge. All right, the integral from 0 to 1, 1 over x to the p dx, that's going to be equal to limit t approaches 0 from plus side, integral from t to 1, x to the minus p dx. Reverse the power rule, we get limit t approaches 0 from plus side, x to the minus p plus 1, divide by minus p plus 1. Evaluate it from t to 1. Now let's apply fundamental theorem of calculus, and we get limit t approaches 0 from plus side. Put the upper limit in, we get 1 to the power of 1 minus p divided by 1 minus p minus t to the power of 1 minus p divided by 1 minus p. And that's going to be equal to 1 over 1 minus p, because 1 to any power is just 1, minus t to the 1 minus p divided by 1 minus p. And don't forget the limit, lim t approaches 0 from plus side. And let's just factor out 1 over 1 minus p and put that in the front. Limit t approaches 0 from plus side, 1 over 1 minus p times 1 minus t to the 1 minus p. So this is equal to limit t approaches 0 from plus side, 1 minus t to the 1 minus p divided by 1 minus p. Let's consider the case when 1 minus p is positive. That's this exponent is a positive number. That means that, of course, p is less than 1. So what we'll have is we have 1 minus 0 to the 1 minus p over 1 minus p. That's the big picture. Now, if 1 minus p is a positive number, this is going to approach 0, because we have basically like 0 squared, which is 0, 0 cubed, which is 0. So we have a convergence scenario. So what we get is 1 over 1 minus p. That means that the integral, essentially the integral from 0 to 1, 1 over x to the p dx, converges and gives us 1 over 1 minus p. And again, we have to stress this. The reason is because this part approaches 0. This part approaches 0, and the result gives us 1 over 1 minus p. All right, so now let's look at another case. Let's consider the case when 1 minus p is negative. So that means that this here, the exponent of t, is a negative number. So that's going to be 1 minus 0 to the 1 minus p over 1 minus p. Of course, 1 minus p being negative means that p is greater than 1. All right, so we know that if 1 minus p is negative, that means that 0 to the power of 1 minus p goes to infinity. Now you might say, how do you know that? Why is that? Well, imagine we have 0 to the power of negative 1. 0 to the power of negative 1 is 1 over 0. That goes to infinity. Or suppose you have 0 to the minus 2. That's 1 over 0 squared goes to infinity. So if 1 minus p is negative, or p is greater than 1, then this integral, the integral from 0 to 1, 1 over x to the p dx, is going to be limit t approaches 0 from plus side, 1 minus t to the 1 minus p, all over 1 minus p. And this part here is going to go to infinity. So the result is going to be infinity. So now that we have considered the case p less than 1 and p larger than 1, let's consider the only remaining scenario when p is equal to 1. All right, so here we have integral from 0 to 1, 1 over x to the p dx, and we're looking at the case p is equal to 1. That means the exponent is 1, so we just get 1 over x dx. So this can be rewritten in proper form, limit t approaches 0 from plus side, integral from t to 1, 1 over x dx. And again, the discontinuity is at 0, and replace that discontinuity by t, and take the limit as t approaches 0 from plus side. This is going to give us limit t approaches 0 from plus side. What is the antiderivative of 1 over x? Well, that's just going to be ln x natural log of x, evaluated from t to 1. Apply the fundamental theorem of calculus, we get limit t approaches 0 from plus side, log of 1 minus log of t. Log of 1 is 0. And take the limit as t approaches 0 from plus side of log t. That's going to be minus infinity. That equals to infinity. That means diverges. Now, I need to really stress this point. The limit as t approaches 0 from plus side of ln t is minus infinity. And that just has to do with the graph of log x, or say the graph of log t. You can see how as t approaches 0, and y equals log t, as t approaches 0 from plus side, the y value approaches minus infinity. All right, let's do a summary here. So the integral from 0 to 1, 1 over x to the p dx is equal to 1 over 1 minus p, if p is less than 1, converges. And the integral will be infinity if p is larger than 1, and we also showed the case p equal to 1, so p also larger or equal to 1 will diverge. All right, now notice that we found earlier that the integral from 0 to 1, 1 over root x dx, is equal to integral from 0 to 1, 1 over x to the 1/2 dx, is equal to 2. Converges. This integral converged. And the reason is because p is 1/2. The exponent of x is 1/2, which is less than 1. Now the second example, we did integral from 0 to 1, 1 over x squared dx. And this went to infinity. The reason is, of course, it diverges. And what's the reason? Is because of the p integral theory, p is equal to 2 greater than 1. So let's do a summary. The integral from 0 to 1, 1 over x to the p dx is equal to 1 over 1 minus p, when p is less than 1, converges, and is equal to infinity, diverges, if p is larger or equal to 1, diverges. All right, let's look at some diagrams here. In this case, we have the first example we looked at was the integral from 0 to 1, 1 over root x dx. And the value we got was 2. That means this is the area, this shaded area is 2. And this integral converged, and we developed the p integral theory, and we know the reason it converged is because the exponent p is equal to 1/2 less than 1. By this I mean the integral from 0 to 1, 1 over x to the 1/2 dx. And this is the p is 1/2, is less than 1. Now let's develop the intuition. We have already done the formal math, but now we want to develop the intuition as well. So you can see how the y equals 1 over root x approaches the y-axis really fast. You can see how it's approaching the y-axis quite fast. And that's the intuition behind the reason that the integral from 0 to 1, 1 over root x dx converges. But notice that the integral from 0 to 1, 1 over x squared dx, diverged, went to infinity. And of course, the reason was it's a p integral. P is equal to 2, greater than 1. But intuitively, you can see how y equals 1 over x squared approaches the y-axis very slowly. For that reason, it keeps picking up more and more area, and the total integral from 0 to 1, 1 over x squared dx, diverges and goes to infinity. All right, thanks.